Current distributes itself in the wires of an electrical circuit so as to minimize the total power consumption. The power P dissipated in an electrical circuit is given by the product of the voltage and current I flowing in the circuit. So for example, the power dissipated as current flows through a resistor is given by the product of the voltage drop across the resistor and the current flowing through the resistor. However, the voltage drop across any resistor, V, is the product of the resistance of the resistor, R, and the current flowing through it, I. So V equals Ri. So that means P equals Ri times I, which can be written I squared R. Now, in this circuit here, we are given the current I that flows in this wire. We are also given the three resistances, R1, R2 and R3. We are interested in what I1 will be. We are interested in getting I1 in terms of I, R1 and R2 and R3, such that the power dissipated in this circuit is minimized, is a minimum. So let's first of all write down an expression for the power dissipated in this circuit. Okay, so I is a given current. It flows into this junction, and I1 flows along this wire here. Now, by Kirchhoff's law, I minus I1 must flow along this wire here, because the currents flowing out of the junction, the sum of the currents flowing out of the junction must equal the sum of the currents flowing into the junction. So I minus I1 plus I1 equals I. Only one current flows into this junction. Anyway, to get the power dissipated in the circuit due to this resistor, we multiply I1 squared by R1. So that's the term we have here. And since I1 flows through this resistor as well, these two resistances are in series, the power dissipated due to I1 flowing through R2 is I1 squared R2, and the power dissipated due to this resistor is the current flowing through it, I minus I1 squared, times the resistance of it, which is R3. Now we want to show that the power dissipated is a minimum when I1 is given by this here. So remember, I, R1, R2 and R3 are given, so they're just constants really, and we have to get the value of I1, well I1 in terms of those constants, such that P is minimized. So in this expression here, I1 is the independent variable. Everything else is a constant. P is the dependent variable. So we want the value of I1, well, we won't be getting a value, we'll be getting I1 in terms of the constants, such that P is minimized. Now to do that, we need the stationary point of this function. So we've P as a function of I1. So the stationary point, or the I1 value of the stationary point, is what makes dP di1 equal to 0. So we have to differentiate P with respect to the independent variable I1. So we have to get dP di1. So R1 is just a constant. So if we differentiate this term, we get 2I1 R1. R2 is just a constant. So the derivative of this term with respect to I1 is 2I1 R2. Now, we could expand this out or just use the chain rule. If we differentiate this, we bring the 2 in front, we get 2I minus I1 to the power 1 times the derivative of what's inside, which is minus 1. The derivative of minus I1 with respect to I1 is the coefficient of I1, which is minus 1. The derivative of I is 0, since it's a constant. And the R3 is just a constant, so that just sits there. So this is what we get. Now, to find the stationary point of our function P, we have to set the derivative equal to 0. So we have to set this here equal to 0. We can factorize I1 out of this, 2I1 out of these two terms, and we also have a 2 by minus, that's a 2I1 by R3. So we can take R3 out of 2I1 here, and then we're left with 2I by minus R3, or minus 2I R3. So we set this equal to 0, solve for I1. So we found a stationary point of this function P, and it's the only stationary point. There's only one solution to the equation dP di1 equals 0, so this must give us what we're looking for. and we can see that we have a local minimum of our function by taking the second derivative of p with respect to the independent variable I1. So we differentiate this expression here with respect to I1. So we just have what's in front of I1 here, which is 2 into R1 plus R2 plus R3, and this will give us 0. It's just I1 doesn't appear in it. Now we compare this to 0. Now since the resistance of a resistor is a positive quantity, well obviously this is a positive quantity, so the second derivative is greater than 0, and we know that when that happens our stationary point is a local minimum. So we have determined the current I1 that flows through these two resistors such that the power dissipated in this circuit is a minimum. So we've determined I1 in terms of the given resistances and this given current I. If R is the equivalent resistance of the circuit, i.e. the resistance of the three resistors, for minimum power dissipation and the corresponding voltage V across the circuit is given by V equals I times R equals I1 times R1 plus R2. We want to show that R, the equivalent resistance of the circuit, is given by this formula. So here's the picture. We want to replace our circuit with this circuit here. So we want this resistance big R to be equivalent to the three resistances in our circuit. Now the voltage V across this circuit is just I times R, and that must be the same as the voltage V across this circuit, so we want these two circuits to be equivalent in terms of V, I and resistance R. Now the voltage drop across this part of this circuit, say from this point to this point here, is the same as the voltage drop across here, because this resistor is parallel to these two resistors, so the voltage drop across the circuit, either across this piece or this piece, is the same, and it's equal to V as the voltage across the entire circuit. So we're looking at the voltage across this part of the circuit, so that's the current flowing through this part of the circuit, which is I1, times the resistance of this part. Well, these resistors are in series, so the resistance of this part is the sum of the resistances of these two resistors. That's R2 plus R3, or sorry, R1 plus R2. Okay, these labeled incorrectly, so we just multiply the current flowing through this part by the resistance of this part, which is the sum of the resistance of these two resistors. So there we have it, I1 times R1 plus R2. So to get the equivalent resistance R of our initial circuit, we just divide across by I. Next we plug in for I1. We found I1 in terms of R1, R2 and R3 and I, so that the power dissipated is a minimum. So we plug that in here. So here's our I1. So we have R3 over R1 plus R2 plus R3 times I going in for I1, and this is what we get, and of course we're dividing by I, so the I goes out. Now we could also get the equivalent resistance knowing what we know about resistors in parallel and series. The resistance of these two resistors is R1 plus R2, and these two resistors are in parallel with this resistor R3. So we know that 1 over the equivalent resistance R is 1 over the resistance of this part plus 1 over the resistance of the other part, which is R3. So if we solve this for R, we will find the result that we got. So we just multiply the denominators to get a common denominator, and then we multiply these together to get the numerator. So we get R1 plus R2 plus R3, and if we invert both sides we get our result as before.